how we can perform the electrochemical analysis by amperometry. So let's see. So first, you make the series of the standard solution. So maybe 1, 2, 3, 4, 5 millimolar, something like that of your species. So assume that you prepare 5 concentration. Then you perform the chronoamperogram. You perform the amperometry to collect the chronoamperogram of each solution. So here you have 5 solutions, right? So this may be the amperogram from your first solution, C1. And then your second solution, C2, will be something like this. Your current is higher, right? Because the concentration is higher. And then from the cocktail equation, you know that increasing C will increase I. Yeah. So this is C1, this is C2, and then C3, C4, C5, something like this. So if you have 5 standard solutions, now you're going to get 5 chronoamperogram. And then what's next? You use the you specifically choose some time tau, some time. This is depend here. You can choose something here or something here as well, but it has to be the same time, the same tau. You choose it, and then you plot the current here, I1, I2, I3, I4, I5, and you plot the calibration curve. I think Ajahn Wali teach you already about the calibration curve. So now you plot the I1 to I5 against its appropriate concentration. So this is I1 from C1, this is I2 from C2, this is I3 from C3, this is I4 from C4, and this is I5 from C5. And then you use Excel maybe or your calculator to generate the calibration curve equation. So this is your calibration curve, and now you prepare the solution of your sample, and then you measure the sample in the same way, and then you get the current of your sample, right? And then you convert back to the concentration. So this is how you perform the quantitative chemical analysis using amperometry. Notice that what we need to really think, we need to think what is the applied potential that we want to apply. For example, if we know that, let's say, what should we use? If we use some compound X which have the formal potential of 0.5 volt, maybe you have to apply like 1 volt or at least higher than 0.5 to get the oxidation, something like that. So you have to apply the potential according to its standard or formal potential. And the second point, you have to choose the time to plot the calibration curve. For example, if you use too long time, like if you choose something like this, so your calibration curve will have the smaller slope, which we don't want it. But if you choose the time too fast, like here, then maybe it has a lot of noise, something like that. So in real life, you have to optimize the applied potential E, and you have to optimize the time tau to plot the calibration curve. All right. So this is the quantitative analysis by amperometry. Let's talk about the advantage and limitation of amperometry. The advantage of amperometry is that it is very easy to perform because you have only few parameters. You have to just choose E and T, E and tau to plot the calibration curve. And the sensitivity is kind of good. Yeah, the slope is not too low actually. But there are some limitations. First of all, it has bad selectivity because from the beginning to now, we talk about only one electroactive species. But what if we have the mixed solution of more than one electroactive species? For example, now we're going to do some reduction. You can see in this box, we're going to do the reduction, right? So we have to apply the potential lower than its standard or formal potential. For the mixed solution of cadmium ion and zinc ion, can we analyze only zinc ion? If we want to analyze only cadmium, then we're going to apply the potential lower than this number, right? Because we want to do reduction, right? We have ion and we want to reduce it to be solid. So we have to apply the potential lower than this. If we want to analyze only cadmium ion, then we apply something lower than minus 0.4. However, if we want to analyze only zinc, can we really do it? In order to reduce zinc ion, we have to apply something lower than minus 0.7, right? Let's say like minus 0.9. But this number is also lower than the standard potential of cadmium. It means that you cannot reduce only zinc ion. You have to reduce both cadmium and zinc, right? You cannot reduce only zinc ion because by that applied potential, you're gonna have to reduce cadmium ion as well. And the amperometry will see only the sum of the current. Amperometry will see the sum of the current. So you cannot distinguish it. So that's why we say that amperometry has bad selectivity. And another limitation is that sometimes it has insufficient limit of detection because of the noise and background charging current, because you can see that at the beginning you have a lot of Faradic current, but you have the noise and charging current too. I didn't show you here, but it is good to know. So amperometry is good if you have the solution of only one analyte, one electroactive species. But if you have more than one electroactive species, it may interfere your analysis. So you may choose to do other techniques, something like this. Any question on the quantitative analysis by amperometry? All right, so with that, let's move to see I think it's the best or obvious application of amperometry, which is the glucometer.